Hello everyone, welcome to the 19th episode of this series. In this video, we'll learn how to go from matrices to something called linear transformations. So in the last episode, we learned about geometric vectors and we learned how to interpret uh, two-dimensional and three-dimensional algebraic vectors as either coordinates of points or geometric vectors denoted by arrows. We also saw a little bit of algebra on the geometric vectors. More precisely, we saw what happens to a geometric vector or an arrow when we multiply it by a scalar or when we add it to another vector. Now, one thing we haven't talked about yet is matrices. So what about them? The geometric analog of a matrix is not an object or a shape in space, but a transformation or a function, if you would like, that acts on vectors or points. Now, this idea is going to be very useful even outside of geometric pictures. Now, some of the examples of linear transformations are rotations, reflections, projections, but we just don't stop here. There's many, many, many more. So formally, given a matrix A, the linear transformation of A is the function TA, which takes a vector V to the matrix vector product AV. Now, because this transformation takes V as an input, if it has to make sense, then the product AV needs to be well defined as well. So this gives us two crucial pieces of information. The first is that the input vector V has to be the same height as the width of the matrix A. And the other is that the height of the output vector AV has to be the same as the height of the matrix A. Okay, so let's look at an example. We're given a 2 by 2 matrix with entries 1, 2, 3, 4. Just by definition, its linear transformation is going to take any vector xy to the product of the matrix 1, 2, 3, 4 and the vector xy, which upon computation becomes x plus 2y, 3x plus 4y. So this TA is a function that takes a two-dimensional vector as an input with entries xy, and it outputs another two-dimensional vector with entries x plus 2y, 3x plus 4y for any values of x and y. Okay, so let's look at an exercise. We are given the same matrix as before, the matrix A with entries 1, 2, 3, 4. We first want to evaluate the linear transformation of A at a few vectors. And in the next question, we want to find a vector V such that TA of V is a particular vector in this question 1, 1. So the first part is fairly easy at this point for us because we've learned how to multiply matrices and vectors together. So because we know what A is, the linear transformation of A is going to multiply whatever input we have with the matrix A on the left. So TA of 3 minus 2 is just going to be 1, 2, 3, 4 times the vector given by 3 minus 2. Similarly, TA of the vector 1, 2 is going to be the matrix A times the vector 1, 2. And similarly, TA of 0, 0 is just going to be 0, 0. So note that no matter what matrix I had here, if my vector was 0, 0, we would always get 0, 0 as an output. And that's actually, as we will learn, a very crucial property of linear transformations in general. Now let's move to the second part. We want to find a V such that TA of V is this particular vector 1, 1. So we know what TA of V is, it's A times V. So we set A times V equal to the vector 1, 1. So we assume that my vector V is given by coordinates x and y or entries x and y. So we get this matrix equation. We multiply the things on the left to get x plus 2y and 3x plus 4y. And now they are forced to be equal to 1. Now the matrix equation on the right represents like a linear system. It is two equations, two variables, and we know plenty of methods to solve it. So I will leave that up to you. And in the end, you will notice that you get x equal to -1 and y equal to 1 as the unique solution to the system. And therefore, the vector that satisfies the given equation has to be the vector with entries -1 and 1. So let's look at another example. We're given a matrix R with entries 0, -1, 1, 0. Then just by definition, the linear transformation of R is given by this function that takes a vector xy to the product of the matrix R and the vector xy, which in this scenario ends up being the vector given by entries -yx. Geometrically, what this linear transformation is doing is it's taking in a vector and it's rotating it counterclockwise by 90 degrees. So if you throw in a horizontal vector, it's going to make it vertical by rotating it 90 degrees counterclockwise. And if you throw in a vertical vector, it's going to make it horizontal by rotating it 90 degrees counterclockwise. This transformation is an example of a geometric transformation, and this is clearly a rotation transformation. Similarly, we can write matrices for reflection and projection as well. Okay, so this brings me to the next type of transformation I want to talk about, namely projections. So the projection of a point V onto a line is the closest point to V in that line. So for example, we have this green line in 2 dimensions, and we have these 3 points in the space. If we were to project these points onto the line, we would take the shortest distance from these points to the line, and where the point that has that shortest distance on the line is going to be the projection. So the way we do it is we draw a perpendicular from the point to the line, and where that perpendicular intersects the line happens to be the projection of these points. Now, projections are useful in many applications because they give us the closest approximation of V by points on a set. This begs the question, how do we actually compute projections? Thankfully, we have a formula. So if L is the line through the origin and the point W, then the projection of a vector V or a point V onto the line L is given by like a vector W times this ratio of the inner products of V and W and W and W. And I do want to point out that this formula is true for all dimensions. Now let's look at an exercise. We're given a line L in the 2-dimensional plane, and that passes through the points 0, 0, and 1, 3. First, we want to find a formula for the projection of any vector given by entries A, B onto L. And then we want to find a matrix P that corresponds to the projection onto the line L. So since W is the vector given by entries 1, 3, the projection of any other vector V with entries A and B onto L can be computed in the following manner. So we compute the quantity V dot W over W dot W times W, and upon a computation, the top quantity becomes A plus 3B. So we're taking a dot product of 1, 3, and AB. So we multiply the corresponding entries and then add them. So we get A times 1 and 3 times B, and we add them. And when we take the dot of W and W, we get 1 times 1 plus 3 times 3. That's 1 squared plus 3 squared times the vector W. Now, this becomes A plus 3B over 10, and we multiply this scalar on the inside. So we get A plus 3B over 10 and 3A plus 9B over 10. Now note that this vector can be rewritten as a product of the vector V given by entry AB and a matrix with entries 1 over 10, 3 over 10, 3 over 10, 9 over 10. And it turns out that the matrix that we are looking for corresponding to the linear transformation is actually this matrix given by entries 1 over 10, 3 over 10, 3 over 10, and 9 over 10. The last thing I want to discuss is an example of a transformation which is not linear. So consider the transformation of a translation f that shifts all points to the right by 1. We want to show that this f is not a linear transformation Tm for any matrix M. Since f shifts all points to the right by 1, we get that f is a transformation that takes in a vector xy and outputs a vector x plus 1y. Now, we want to show that this is not a linear transformation Tm for any matrix M. So we're going to prove this using contradiction. So we're going to assume on the contrary that f is indeed equal to Tm for some matrix M with entries A, B, C, D. If that is the case, then just by definition of a linear transformation, ABCD times xy has to be equal to x plus 1y for each value of x and y. However, if I take particular values of x and y and I take them to be 0, we end up getting that this input vector is 0, and as we discussed earlier, the left-hand side will end up becoming 0. So if we just look at the first equations in the product, it's going to be ax plus by, but it's going to be 0. But on the right-hand side, we have x plus 1, which becomes 1 when x is 0. So what we've arrived at is that 0 is equal to 1, which is obviously a contradiction, and therefore our assumption was incorrect. And as a result, we've shown that f cannot be equal to Tm for any M. And with this, I would like to end this episode. Hopefully things made sense. I am going to see you guys soon. Up until then, happy learning.